Example 16.5 is going to introduce our second parent function in the rational functions section. It'll be the last one that we do. It is called the reciprocal squaring function. So it's going to be very similar to the reciprocal function, but it's going to add the element of squaring to it as well. And you can see here with the equation, it says 1 over x squared. So we would have to square the x first, and then take the reciprocal of that particular value. The rest of the instructions are just like what we saw in example 16.4. We're expected to define g over the largest possible domain, and we're going to use a t-chart to be able to graph g, and then we'll also use limit statements to be able to describe the arrows on the graph. Let's get started with the definition. Since all we've done here is taken x and squared it, in terms of it being different from the reciprocal function, the domain restriction is still the same, and that would be a domain restriction of 0. So I'll define g colon negative infinity to 0 union 0 to infinity. This is what maps to other real numbers given by g of x equals 1 over x squared. So there's your function definition. Now we would want to go through and make a table, and we'll have x, g of x values, and I figure we might as well use the same x values that we did on the reciprocal function. If we don't need as many, then we can always not plot as many, but we'll start off with this. And we can also go ahead and say that with 0, this is going to give us a undefined result. With 1, so here's the process. If you think about it from an operation standpoint, it's just whatever the number is squared, and then you're going to be taking the reciprocal of that. And so when you plug it in, and this is what it looks like, 1 over 1 squared, which is just going to end up being 1. For 2, if I was to do 1 over 2 squared, I would end up with 1 over 4. So you have to square the number and then think of it as the reciprocal. So for 3, I should be able to jump straight to the answer. If I square 3, I get 9. Reciprocal of that would be 1/9. So you can go through and actually plug them in individually and see how they come out, or you can recognize the pattern with the squaring and then the reciprocating, and that will make it go a little bit faster. So for example, with 1/2, 1/2 squared is 1/4. The reciprocal of 1/4 is positive 4. 1/3 is going to map to 9. Now, that takes care of all the positive x's that we've picked here. For the negative x's, we're going to end up with the exact same result. Because if we think about what happens with, say, -1, 1 divided by -1 squared, as soon as I square -1, it's going to end up giving me positive 1, which is going to just give me 1. So all of these negative x's are going to end up mapping to the same y value that we have for their positive counterparts. That means -2 will map to 1/4, -3 will map to 1/9, -1/2 will map to 4, and -1/3 is going to map to 9. Let's plot these points. I'm going to start with the positives. 1/3, well, 1/3 9 is not going to fit on the graph, so let me go 1/2 4. My window's just not big enough for that. 1 1, 2 1/4, 3 1/9. And I have a very similar kind of curve in the first quadrant here, like I did with the reciprocal function, and that's going to still have the horizontal asymptote, and it's still going to have a vertical asymptote. The vertical asymptote is going to go all the way down the graph, and the horizontal asymptote is going to go all the way across the graph. The equations for those will be x equals 0 for the vertical asymptote, y equals 0 for the horizontal asymptote, and then I'll do my best to connect the points in a nice smooth curve. Again, using the asymptotes as the boundaries for my curve within the first quadrant there. So that is the portion of the domain represented by 0 to infinity. Now there should be another curve to go with the negative infinity to 0, and that's going to be from the negative x's. So I'll have negative 3 1/9, negative 2 1/4, negative 1 1, and then I'll do one final point at negative 1/2 4. Then I'll connect things together best that I can. And that gives me the part that goes with negative infinity to 0 from the domain. So all of this together represents the whole function. So our whole function here is g. Not in the first and third quadrant, it is in the first and the second quadrant. As far as the limit statements are concerned, there are still 4 limit statements. Y approaches something as x approaches infinity. Y approaches something as x approaches negative infinity. Y approaches something as x approaches 0 from the right. And y approaches something as x approaches 0 from the left. So again, the first two statements are going to be similar to the in behavior statements going off to the right and going off to the left. So we'll put arrow number 1 here to the right, arrow number 2 is here to the left. I'm just doing this for learning purposes. You don't necessarily have to do this for yourself. It's just a way to help keep track of which statement goes with which arrow. If you don't want to put these on your graph, that's fine. So going off to the right and going off to the left, we're going to be getting closer and closer to the horizontal asymptote, which has a y value of 0. To the right and to the left of the vertical asymptote, we have statements 3 and 4 and arrows 3 and 4. Now both of these arrows are going up, up, up as we get closer to the vertical asymptote. So I would say that each of these have y approaching infinity as x approaches 0 from the right, and also as x approaches 0 from the left.